Good morning, good day, and good evening. I'm, as always, your host, Brody Robertson, and today we have the developer of a project on that I don't know, I'm sure a lot of you've probably heard of, but maybe haven't had a chance to use just yet. Is it pronounced ZLUDA? Because that's how I've been saying it.
It's a very good pronunciation. It's not 100% correct, but I don't think I can give Polish lessons to the whole world. So let's say with ZLUDA.
You can
So
certainly try. How would you
it's good.
say it if like you're trying to say it correctly?
Well, it's written incorrectly, but you would pronounce it ZLUDA.
Ah, okay. Yeah, I was never going to get to that from the way it's written.
Yeah.
So, how about you just introduce yourself and we can go from there.
So I'm Andrzej, Janik. It's nice being here. I'm a software engineer. I wrote ZLUDA. I'm still working on ZLUDA, and hopefully I'll be still working on ZLUDA in the near and far future. Hello.
Hello.
Yeah, and I have my tea because
You do.
I heard it's a requirement for this podcast.
I didn't even
It's in the
mention
name.
it, but yes, I
It's in
have
the
mine as
name.
well. Yeah, it works. Hey, look, if you actually bring it, you are better than most of the people, and better than me most of the time as well. Yeah, so I'm gonna try to not look really shiny right now because it is. I'm in Australia, and it is
Oh,
9:30
what
p.m.
time is it?
Yes, it's
Okay.
9:30 p.m. and it's still 29 degrees Celsius. So.
Oh wow.
Yeah, if you notice me looking shiny, that's gonna be
Crazy.
why. I've got my fan on, but we'll see how it goes. Hopefully it cools down a bit later. Anyway, enough of me complaining about the terrible weather here. I guess we can just start with what the project actually is, and why was it initially created?
Oh, starting with
Those
the
are
hard
two
questions.
difficult questions, yeah.
It's a long story.
What
It's
it
a long
is easier,
story.
I think.
Hopefully, I will get to the end of it before you collapse from the heat. So basically, it started because I thought I will not get in trouble writing this project. So it went wrong from the day one. So it started when I was working at Intel. So I was working at Intel on a certain project, which okay, it will remain unnamed. Let's call it Project X.
Sure.
I worked on Project X with, and those two guys are important for this story. Alexander Lyashevsky and Alexei Titov. They are grandfathers of this project. So work at Intel. It was a so some details I can provide. So it was a project, certain GPU library for a certain workload, for obviously Intel GPUs. Was one of the first projects actually using Intel SQL implementation called DPC++. So we can think of it as sort of Intel's answer to CUDA. This was a very early version of SQL, and we had a lot of discussion about, well, how useful it is, how good it is, and there one of those discussions or arguments. I don't remember who, Alexander or Alexei, told me something that stuck with me. Is that okay? SQL might be good, might not be good, but what our customers want, they want CUDA. They want CUDA. They want CUDA on Intel GPUs, and I don't remember what we discussed in detail, but it really finished this discussion. So he was right. I had no comeback from this, but the thought stuck with me. So time passed. The Project X was cancelled, and I started working as a manager. As a manager, I had almost no opportunities to write code, and it started to become slightly frustrating. If you don't write code, you sort of become every day you get slightly more diverse from the daily realities of writing code, especially if it's a Intel GPU code, where at the time, so it was pre what is the public name, Alchemist.
Mhm.
It was still in flux, still moving quickly. So I was getting a little bit more frustrated, and 2020 came in. With this COVID, we're all stuck inside our homes, me included. And at the same time, Intel, when it comes to Intel GPU development, started moving to a different host code library. So
Mhm.
previously, most of the development used OpenCL, but OpenCL is relatively high level, and if you want to have some kind of extensions to OpenCL, you have to some degree negotiate with other vendors. So
Mhm.
you don't create something that is useful to you, and another vendor comes something useful to them, and there are just very minor differences.
Mhm.
So Intel came something we've called level 0. This was the new premier way to write host code, and it looked fairly good, and we're all just starting to use it, starting to learn it, and I wanted to know more about it. So in my mind, I had two choices: either resurrect Project X, which was cancelled. I was specifically asked not to do this in the open source, and I thought, well, okay, if I do this, I'll get in trouble. And there's another project I thought would be interesting, implementing CUDA on top of level 0.
Mhm.
And my thinking at the time was, okay, well, what I really wanted to do was learn level 0, understand how it works, what I can do with this that I cannot do with OpenCL. Um, if it works, well, it's not going to work, but if it works, it's going to be very cool.
Mhm.
So I started working on it, and I worked on this through most of the 2020. And well, that's how ZLUDA came to be.
Mhm.
Surprisingly, it worked. Surprisingly, it reached decent performance,
Mhm.
and I released it sometime late 2020.
What would be decent performance in your mind? Like, if you were to take an equivalent NVIDIA GPU and an Intel GPU, like, what percentage of the performance were you sort of getting at?
Right. So this is a difficult question. It's
I
very
guess it depends
difficult
on the workload,
to
yeah.
difficult to compare the performance, because you need a workload where you have implementation, native CUDA implementation,
Mhm.
and OpenCL implementation
Mhm.
that works natively on Intel. A good target was Geekbench. That's why Geekbench was pretty much the only thing that was working. So in my mind, something like 80% of the native OpenCL performance would be really good,
Mhm.
surprisingly good. I don't remember what was the exact performance. Was like something like 90%. So Geekbench is actually a suite of tests. So,
Mhm.
so some surprisingly, some tests were even faster than the native versions. Some were
Wow.
slower, but the performance was, I think, around 90% overall, which was much better than I expected.
Well, it's much better than the alternative, which was 0.
Yeah, yeah, yeah.
So, for anyone who may be unaware of what ZLUDA actually is, like, at a high level, can you just explain, like, what the general purpose of the project is?
Like, general purpose of the project is you have your software, and your software doesn't work on your hardware. So ZLUDA makes your software work on your hardware. That is.
Okay, maybe
And then
maybe a bit lower level than that.
yeah, yeah, no. But, so you understand what is the uh, good about this project, and specifically targets applications, libraries, whatever plugins using CUDA. And
Mhm.
the reality is, if you have your GPU and maybe use your GPU for gaming, which is horrible. Why would you do this? GPUs were meant to multiply matrices. GPUs were meant to calculate chemistry and physics. So if you have a gaming workload, well, if you have a game, then you're going to use a specific API to do things that game do. I don't know what they do.
Generate polygons.
So things like DirectX, Vulkan, OpenGL. But if you want to do computations, so physics simulations, chemical simulations, whatever, machine learning, then you have specific APIs for compute, and by far the biggest one is CUDA. And think about CUDA, it's written by NVIDIA, it's created for NVIDIA's GPUs. But it turns out, and this is what ZLUDA does, you can implement the runtime environment of CUDA and then run some other GPU from another vendor. You can use your application on another GPU, non-NVIDIA GPU. From the perspective of the application, it's a normal NVIDIA GPUs. It's slightly strange, has a little bit strange configuration. Some things doesn't work, but from perspective of an application, it's the same. It's similar to how Wine works,
right.
on Linux. You can run Windows applications on Linux.
So there's something I was going to say.
And then okay, and
no,
maybe,
I had something. I just completely blanked on it.
Lower level explanation. So if you have a CUDA application, so for those of you who wrote CUDA, they might be thinking, okay, how is it possible? Because if you write CUDA is also CUDA is many things, but other than the runtime environment, it's also a programming language. So you write your program in CUDA. It's a dialect of C++, and you can you can mix GPU code and CPU code. But this is an illusion, because what happens at the end, at the sort of bottom level, and that's where it lies, you have it's a normal application which calls into NVCUDA DLL or libCUDA SO. It's a normal application which uses certain functions provided by a certain library. There's no magic. And if you implement this runtime driver library, then you can then you have ZLUDA. ZLUDA implements this library, and this library can be relatively complex because you need things. So what runtime library does, it allows you to control your GPU. So you can query your system. Okay, I have GPU number 1 with this name and with this much RAM with this, and we have this many flops. I have GPU number 2 or 3, and on this GPU I can allocate memory. On this GPU I can execute a computation. So runtime also contains a compiler for virtual assembly. This is a bit more complex, but you have to also provide this. And ZLUDA does it.
So obviously NVIDIA likes, CUDA being on the NVIDIA GPUs. Were you ever concerned with NVIDIA having any issue with you doing this, or?
No. So I had initially, but the case has been settled with Oracle versus Google, and I have been contacted by a fair bit of organizations. I mean, initially including Intel, and pretty much everyone tells me they checked with their lawyers, and lawyers think that after Oracle versus Google, implementing APIs is fine. You can just do this. And actually, I saw this when I was at Intel. So I released end of 2020, next version early 2021. I don't remember how much later, but I think 3 months later, the Oracle Google was settled. The judgment was made in the United States Supreme Court, and shortly after I was contacted by Intel, and they told me, "Hey, Oracle Google is settled. We think we can do this."
Yeah, I know about that case. I didn't realize it was only settled that recently.
Yeah. It's
Jeez.
well, 2 years ago.
Yeah, well, yeah, it's still pretty recently. Like, when did the case actually start? If you remember what year? It was like early.
I don't know, maybe 2018, 2019. Those cases take a long time.
Sure, yeah. But basically, you had just effectively assumed like, okay, that case has gone well. Now that it's actually
Yeah.
done, it's just
Yeah.
like,
By the way, I'm not a lawyer. This
I'm
is
not
not
a
legal
lawyer
advice.
either. This is neither of us are lawyers here, so don't take anything we say. Why is the camera following me? Don't do that, Jitsu. Yeah. Don't assume that nothing we say is legal advice here. Oh no,
Yes.
now where is it even focusing? Oh, it's off there. Is it gonna move? No? What is it? I hate Jitsi so
I don't
much.
know. On my screen, the camera is fixed.
Oh. Okay, sure. Okay, I'll just fix it up on here then. Fine. Anyway, getting distracted by that.
Yeah, technology is hard.
Yeah. There's probably a setting to turn that off. I just don't know where it is.
Yeah.
So what is it about CUDA that makes it such a driving force in this space? Like, why does everybody want access to CUDA? Is it just the fact that NVIDIA has that market share now, or is there more to it than just that?
Oh, there's much more to it. So if you look at how the current market for server GPUs look like for GPU compute, so you have three vendors, right? NVIDIA, who is competent, and Intel and AMD, who are not. And I'm talking about software because that's my expertise. Well, I can't really speak much about hardware. Hardware looks fine from other than some embarrassing failures, so the hardware looks fine. But the problem is with the software. So you are a developer, then you expect a certain level of quality in your software. So your compiler will not miscompile your code. Your profiler will give you profiling information. Your debugger will work. And those things are, for some reason, possible in CUDA land. They're totally possible in HEAP land and DPC, whatever it's called, Intel land. And that's it. Things just work on NVIDIA. So it's not like NVIDIA stack is perfect. For example, we run into a miscompilation in the NVIDIA compiler. So they have their own bugs, but it's like things work. You have profiler, it works. You have compiler, it works. You have debugger. So I can specifically talk more about AMD, because at Intel I was working in pre-silicon environment. So there's expectation that things will not work. So I didn't really use the public versions much. But on AMD side, so imagine that your runtime, for example, operation on images doesn't work. Like silently give you wrong results. So, and it's arbitrarily for only just some formats. So we have image with floating 32-bit floating point pixels, it works. If it's 16-bit floating point pixels, you get wrong results for no good reasons. You have 8-bit unsigned integer, it works. 8-bit unsigned works, signed gives wrong result for no reason. And this sort of thing. Like you just cannot live the life where you have to second guess everything you do with your compiler. And some tools are just not usable. So if you're writing GPU code, you're not doing this for your deep love of GPUs. You do it because you want to have performance. And what you need a profiler. You need a profiler to tell you, okay, what are my performance problems? And you're going to use it a lot when writing GPU code. I think an average GPU programmer have a higher need than average CPU programmer. So so an example on AMD performance profiler. So you want to profile a workload, and the workload will have, let's say, performance events, and let's say coarse-grained performance events, meaning copying data between CPU and GPU, and dispatch of a kernel, and some other things that take time on a GPU. And in a normal workload, you will have tens of thousands, hundreds of thousands, maybe low million number of those events. And you open imagine this. You open a AMD GPU profiler, and while it has certain limitations, it can only capture a certain number of performance events. So I want you to guess how many it can capture.
If you were talking about dealing with like millions, I would hope that you could handle that much. But if there's a problem here,
Bit less.
maybe in the range of a few 100,000.
50.
Oh,
50.
oh, okay.
That's the limit. At least it was last year when I was using it. So you cannot measure performance.
I see. That sounds like a problem.
It's a problem. I think they improved it, and you can now capture low thousand, maybe low hundred.
Okay.
I mean, it's better, but it's still
Orders
not.
of magnitude better.
And yeah, but still, if you have NVIDIA profiler, you can just capture the things. I only work with smaller workloads when it's maybe tens of thousands, and it just works. So that's it's more of an AMD problem. So I mean, going back to a higher level, if you look at AMD, they have the right strategy, and bad execution. Where Intel had bad execution, have bad strategy, but I think decent execution of the strategy, and CUDA works. So let's talk more about Intel. Like, I want to talk more about Intel because right now they are poor. There's no risk that they're going to sue me, and Intel has the so if you look at what AMD is doing, their compute stack is relatively similar to CUDA, meaning the goal here is you have your CUDA code, existing CUDA code, and porting to AMD world is, if it works, it's relatively easy. You
What
have
is
to rename
the
functions.
AMD? Yeah, I was gonna ask, what does the AMD stack actually look like?
It's they're following CUDA basically. So the APIs are the runtime, the performance libraries are relatively similar. The tools might be different, but the tools are not super important. They're not part of your program, right? So imagine you have a function to allocate memory. On CUDA side, it would be called qmalloc. Take some arguments. On AMD side, it's going to be pretty much exactly the same, but it's going to be named heapmalloc. And this is what programmers actually want, because the world we live in is the world where most of the GPU compute code is already written and using CUDA. So this is objective reality. Intel rejects this objective reality and lives in their own dream world where there's no GPU code and every programmer wants to write code from scratch. So if you look at their deep C++ or SQL, in some ways it is actually better than CUDA. If you look at the purely at the APIs they have, but the problem is the API is very different from CUDA. So every porting you do, it's one-way ticket to Intel Ghetto, and it's there's also the social aspect. somewhat difficult to trust Intel, who hasn't seen much success in GPU compute world, to port to Intel platform and just abandon your existing working CUDA code. With HIP, you can always port back HIP to CUDA. You can do this. With DPC++, it's much more difficult. It's very different. And another problem with DPC++, it's very strongly C++ based. With CUDA and HIP, you can have your application written in some other language, and it's going to interoperate with your CUDA C++ code relatively easily. Because so there's a C API which you can use from any language. With DPC++, it's not so easy. Everything is C++. There's no C API. So using it from something like Python is a tad difficult. And even if you do the mapping, it's very difficult to have interoperability between your back from C++ to Python. And we are talking about C++ and Python, but there are other languages that also want to do some degree of GPU compute, and they have the same difficulty. And you're not going to be able to interoperate between all of them, and you need to have strong C++ support. So it's already a sort of losing position. So this strategy is just not good. It has no future. Unless we port ZLUDA to Intel GPUs. Hopefully we'll do this soon and rescue them from their own wrong ideas.
Yeah, when you bring up supporting things like Python is a really popular language when it comes to like doing that in like the research space. You have a lot of people who just
machine learning.
They're already doing a lot of their math computation with Python, and they're going to do a lot of their other stuff with Python if they can. So it just makes sense to make that, or make it easy to interact with other systems through that as well, where this Intel system sounds like it's a whole different way of approaching things that adds some extra challenge.
CUDA makes it easier. Like Python is actually in a relatively good spot because, as I understand, they have some good ways to bind to C++ libraries. Other languages are not in such a strong position.
Right, sure, that makes sense.
So it's slightly less of a problem from Python perspective.
Okay, so we kind of went down. I don't even know how we exactly got to this bit. But let's shift focus a little bit. So now that the project has been through its like new revival into what it is now, what are the current goals of the project? Like, what sort of applications are intended to be supported, and what would be like a dream support that maybe right now is a bit outside of the scope? And then what are things that you could support theoretically, but you're just not going to touch?
Right. So the main goal didn't change. Total world domination still is something we want to do, but more specifically, since our team is relatively small, just me, and external contributors for whom I'm very thankful. So we have to. There's limited amount of time, so we need to focus. So right now we are focusing on machine learning workloads, all the PyTorch, TensorFlow, starting with something similar like LLMC, that we want you to be able to, whatever machine learning workload you have, to run smoothly on ZLUDA. And we're also making some other choices. So we are focusing less on Windows, because on Windows needed extra support, and it's going to work, but you will have to do user. It's not going to be as smooth. It wasn't really smooth, but it's going to be even less smooth. We are going to support less GPUs, only focusing on the GPUs that are sort of similar to NVIDIA GPUs, and this is specifically RDNA GPUs, RDNA 1, 2, 3, future RDNA GPUs. Yeah, these are the main areas of focus.
What is it about the Windows support that actually makes it a challenge?
Right. So loading libraries. It's tricky. So in the perfect world, how it would work? You have your executable. It doesn't matter what sort of executable. It doesn't matter if it's Python or I don't know, or Blender or something else. Language is not important because at the bottom level you are talking to a library. You launch your exe through some kind of ZLUDA launcher, and every time you load a library, we check, is it a CUDA library? If it's a CUDA library, we replace it with ZLUDA library. So it's all transparent and efficient. But and every time you launch a new subprocess, we also insert ourselves into the subprocess, and if the subprocess loads a library, we also replace it with ZLUDA library. It's turns out it's not really possible. So what ZLUDA launcher settled on is, and why it's not possible. Firstly, surprisingly creative ways you can load CUDA into the process. So some applications will have the main exe will have dependency on the NVCUDA DLL, and no, we can replace it. It's fine. But some other applications, and it's relatively think of things like Python. Python actually doesn't have dependency on NVCUDA DLL. It's just some Python script is going to load NVCUDA DLL using dynamic loading APIs, load library. So okay, we can overwrite your load library and replace the libraries, but there's also some applications where you load DLL, and this DLL has a strong dependency on NVCUDA DLL, and we cannot detect this. On Linux world, it's slightly cleaner because anytime you load a library, the system runtime loader will go through the public API. It will be a call to DLOpen. On Windows, it's split. If you're doing it yourself, it's public API, but the system loader will have its own function, and we don't want to overwrite system functions from kernel 32 DLL or whatever. It's not a robust way. So what we settled on, you run your application under ZLUDA loader. ZLUDA loader will inject our own NVCUDA. You want it or not, you are getting it, which is already not nice, but presumably you want this. And then if you are explicitly loading library, then we explicitly replace it. If you are explicitly loading NVCUDA, we're overriding it to explicitly load our own NVCUDA. Just this part of implicitly loading ZLUDA into every process, whether it's necessary or not, it's sort of not nice, but it's most robust way. And you need to have this support for every DLL, and those DLLs, there's some degree of complications, because also you have sort of two kinds of DLLs on Windows when it comes to CUDA. You have loader DLL, which lives in Windows System 32, and you have real library, which lives in one of those driver paths. On Linux, it's simpler. You don't have this loader DLL, and Linux give you sort of official supported way to inject yourself into process and all its children through environment variables. So it's less work. It's less work, just and it works.
If you could just suddenly force all the Windows developers to do things in a certain way, what would you want them to be doing?
I don't want to force them to do things my way that is easy to me, because they just have different. It's different system, different needs. So, like this is kind of baked into the system, the way the dependencies are resolved, and like it's more difficult for ZLUDA, but in some ways it's actually better than on Linux, because on Linux you have a dependency to a function. So if we say the simplest function there is malloc, right? So on Linux it's going to be what is baked into your executable or library is the name of DLL and the name of the function. On Linux side, it's just the name of the functions. Your dependency, your name of the library is not included in the dependency resolution, and it quite often leads to conflicts. So, I mean, for my purpose, the Linux way is easier and smoother, but it has its own problems.
Mm-hmm. That's understandable. It does sound like, though, that the Windows side just makes things more complex. Like it sounds like
For me, yes, yeah, because what we do is not normal way of doing
sure,
things.
sure,
Because what we could do alternatively, just throw away your NVQ, your official NVQ.dll, and just install ourselves into Windows System 32.
right.
But I don't want to do this because it can crash some applications. Maybe we don't support something, and even if you don't have an NVIDIA GPU, it's going to be more robust if you use official library, because there's some hidden APIs, there's dark API. We might come to this in our discussion, but if it's not supported on our side, your application is likely to crash, and it's going to happen with games.
Mm-hmm.
So suddenly you installed ZLUDA into your system, and some of your games start crashing for no reason, and it doesn't show it's fault of ZLUDA. It just crashes, and you don't know why.
Mm-hmm.
We don't want to do this. We want you to launch your application with ZLUDA launcher, so if it crashes, you know it's ZLUDA. It's not something else.
Mm-hmm. Mm-hmm. No, that actually makes a lot of sense, because my understanding is there are certain parts that you don't, at least right now, want to bother touching, just because, you know, as you said, there's only so many people working on the project. There's only so much time to work on things.
Yep.
So there's things that just are not going to be included, at least for now.
Yes. That's if you look at the NVIDIA API, not NVIDIA. If you look at the CUDA API, it's huge. It's gigantic, and you know it's 80-20 thing. If you look at application, they're going to use certain functionality much more than any other functionality. So pretty much every application will want to allocate memory on a GPU. Mm-hmm. Every application will want to launch kernel. Not every applications will have multi-GPU support. Not every applications will want to do runtime linking of kernels and some other niche functionality. So generally, how we approach things in ZLUDA, we look at so we don't track CUDA version and add APIs added in a CUDA version. We look at applications, and if application uses certain APIs, then we implement those APIs. Mm-hmm. And next applications, what API does it use? We implement those APIs. So sometimes I get a question, which version of CUDA is implemented in ZLUDA? I don't know. It's whatever applications are using. It's a mix. Mm-hmm. We want applications to work. We don't care about some, some artificial standard that doesn't exist.
Mm-hmm. Right. Actually, that's I think a really sensible way to approach it, because, like, you know, you could approach it as, I don't know how CUDA versioning works. Let's just say version 1. Like, start at version 1, get a complete perfect implementation, but then nothing else, like no modern applications are supported because all you're supporting is like that basic core functionality, and you're going to take a really long time to get to the point where things are actually working with real world like software.
Yeah. Yeah, we care about application. We want your stuff to work. That's the goal, whatever it takes.
Right. You're not trying to pass like Vulkan conformance tests.
No.
So you bring up that term dark API. You said that as one of the things you want to talk about. I've never heard that term before. What does that actually mean? And then we can go into like what you're actually talking about with CUDA dark API.
Yeah, it's a pain. So something you should understand. So CUDA obviously not an open source API, but there's something more to it. Is that your code is always a second-class citizen on CUDA platform. You may not realize it, and I will explain why. So first thing, there's really 2.5 APIs on CUDA. So there's 2 APIs most CUDA engineers will be aware of. There's what they call runtime API and driver API, and they're extremely similar. Runtime API is slightly higher level, driver API is slightly lower level. We implement driver API. And there's also one more API hidden from a public view. So we have API. Typically, if you have API, you have a name of a function, number and type and name of the parameters and the return values and some documentation. With Dark API, you have nothing. Every function that is supported by Dark API is some kind of unique identifier, git, and the index. So you ask your runtime, you ask your CUDA driver, hey, give me table with function pointers for this unique key, and this is used by Intel runtime, really for no good reason. I don't know why they do this, and for some first-party libraries, because there's some things NVIDIA doesn't want you to know and be able, or they don't want you to be able to do. And a classic example is ray tracing. So if you look at, so you might think, okay, I have my GPU and I want to know if my GPU is capable of hardware ray tracing. And CUDA doesn't expose this information, at least doesn't expose it to you. It exposes this information to its own libraries, its own runtime, and it goes through this hidden API. It has no name, has no documentation, so we call it dark API. I don't know what is its proper name. It's nobody knows. And the dark API is frustrating experience for someone for something like ZLUDA, because we have to implement it. It's actually almost kills ZLUDA, because first time I'm enabling very simple application, just adds it adds 2 numbers. All it does adds 2 numbers on a GPU. So I have this CUDA application, and I look at the interactions between application and CUDA driver, and everything goes as expected. Every function that I wrote in the source code is being called, and there's one small addition I did not write, and there's call to this Q export table, and I look at it. It's some kind of unique key I never seen before, and this gives me a table of pointers. I don't know what are those pointers. Okay, I set breakpoint on each one of them, and it calls one of them with, for some reason, I know no arguments. I don't know what this function does. I decided that's too much for me. It's too much for me. I give up, and I gave up for, I don't remember, for 2 weeks. And after 2 weeks, I thought, well, okay, maybe, well, I'm in mood for some pain. Let's try it. It's probably not going to work. And I look at this function. Actually, look at what function it calls, and it's 4 instructions. It calls allocation. It calls malloc to allocate some memory and returns this memory to the driver. Okay, I thought, well, it's not so bad. Actually, and it's really motivated me to keep going, and pure luck, because it was by far the simplest and easiest function from the Arc API. All other ones have been slightly more difficult. And generally, so generally I don't, and it was wrong approach to look at what this function does, because it's most of the time it's not super useful. Nowadays, what I do, I look what are the inputs and what are the outputs, because usually that's your first clue. If a function returns some kind of pointer, and you see across the rest of the application that this pointer is used as context, then you know, okay, this Dark API is creating context with some internal bits being set or unset. And those bits are not really important. We might as well create a context for ZLUDA, because it probably does something, but there's no, across the applications we had, there's no observable effect to this function that is different from the public API. So that's how it goes. And we implemented those only parts of the Arc API that are necessary to run your applications, mainly interactions between the high-level runtime API and driver API. Runtime API doesn't always talk to driver API through the public APIs. It also talks through Dark API. And then I noticed that the first-party libraries use Dark API for various reasons, which I don't care about.
So it's basically just those internal functions that there's no point for them to document, because you're never actually supposed to call them yourself.
I mean, I think they should document them.
Well, they should,
because it would be nice to to use to know how can I use everything that I paid with this GPU, but they decided not to. There might be some thinking why they do this. I mean, it's obfuscation. Maybe some of those things they just don't think are useful. Maybe some things they just want to hide. Well, when it comes to ray tracing, they definitely want to hide those things, because optics also doesn't expose those things.
Whatever the reason for it, it makes your life a lot more complex.
Yeah. It probably makes also life of CUDA engineers more complex, because some things they do in this Dark API, I don't know why they are doing this. It's just, for example, there's something they added recently, and my suspicion is they wanted to make my life more difficult, but compiler optimized out all they wanted to do in this function, because this function, what does it do? You have, let's call this function foobar, and it returns if function foobar, so itself, starts at an even or odd byte in memory.
Okay.
And this is completely totally pointless, because your compiler will pretty much always align your function to not only to even address, but most likely to your natural size, to 64 bits. So it's always going to return 0. I don't know why they do this. It's just mystery to me. And literally 2 instructions, or 3.
I don't know. I don't. I have an answer for you either.
But my expectation is there was more complex body inside they wanted me to implement, but optimize everything out. Who knows what they are thinking? It's mystery. I only care about applications running, not about their creative ideas.
Right. So with these Dark API functions, the way you're basically approaching them is effectively like a test suite, where you're throwing data into it, you're looking at the data that comes out of it, and you're hoping that whatever you're doing in between is getting you the result that would happen on an actual NVIDIA GPU with CUDA.
Yeah, most of the time it's sufficient. Sometimes you have to look what it does internally. But it's usually too complex to do this because it can, if you have a function, it's going to call any number of internal functions. So observable properties is what matters.
Mm-hmm. That
Like if it set a flag, if it sets a flag in some kind of object, it tells me nothing.
Mm-hmm.
We're going to do the same thing without setting this flag.
Mm-hmm. So you said earlier that CUDA is a really big API. How big actually is it?
I can open my. If you give me a minute, I can open my ID and tell you.
It's all good. It's all good.
Just give me a second. So just it's not 100% accurate. It might also count some function pointers, but it's just the driver API is 575 functions exported.
Okay.
We don't implement all of them. We implement, well, currently we implement nothing, but the old ZLUDA implemented below 100, or maybe slightly above 100, and it was enough to run a lot of applications, most of them.
Okay, so
this is driver API, and there's also performance libraries which have their own APIs, and they also have a lot of functions.
So those 100 are like a lot of the main functions that sort of everything is going to need to deal with. There's going to be a lot of these like little functions here and there that like that are important for those workloads, but may not necessarily be something that most applications are using.
Right. If you have, we implement, as I said, we do enablement workload by workload, so application by application, and we can say that there's a core of operations functions that everyone is going to use, and then it gets less and less common. Some of them might be used by nobody because they are, added for completion, some kind of getters of properties, this sort of stuff.
One thing I didn't really ask earlier is like, what does the name of the project actually mean? Like, why is that the name? I kind of get like it's UDA, so CUDA, but like, why ZLUDA?
Yeah. So, okay, I have to give excuse for myself. So
Okay.
The name of the project, I literally came with it day before release. Initially, and for whole of 2020, and you can say it if you go back enough in history, it was simply called not CUDA. And I'm not a lawyer, but I'm relatively certain that I cannot release project name like this. And the day before release, let's go with something that sounds slightly like CUDA. There's no such words in English, I think, really. Let's try Polish. I'm Polish. And this sounded nice. So ZLUDA means something like mirage, illusion.
Okay, that's actually, that sounds kind of cool, actually.
There's no hidden second meaning. I thought it's going to be nice. Use Polish. Have a word that sounds nice.
And it's not going to get you sued.
Yeah, but I was aware that it's going to be impossible to pronounce. So it's spelled differently. So I simplified it a little bit.
Yeah. Yeah, as I said, like I was never going to pronounce this word correctly, but I don't think anyone was going to. If it was spelt correctly, how would it actually be spelt?
I can write in chat.
Oh yeah, let's see if I can bring that up. I don't even know what that's.
Yeah. This L is spelled differently.
Okay. No. I don't even know what that symbol is.
It's like English W, the pronunciation.
Oh, for anyone who is just listening, it's an L with like a slash through it.
Yep.
Yeah. I have Polish listeners who will be like, "You're a moron." What are you talking about? I can barely speak English on the best of days. I'm not. Don't get me started on Don't get me started on Polish. That's what I get for being Australian. Yeah. So, where do we go from here? Oh, we actually haven't talked about the talked about it being in Rust yet, have we? I don't think.
Yeah, I get this question a lot. So Rust is being perceived as still sort of exotic alternative to more mainstream language in this area for solving this sort of problem. So the mainstream solution would be to C or C++, but the thing is, I have known Rust for a long time, for over a decade. So I learned Rust before version 1.0.
Yeah, I was gonna say if you've known Rust for over a decade. Yeah. Okay.
So
Yeah.
I've been interested in this early because I always wanted to do. So professional, I've been writing C# and then F#, but I always had certain level of interest in lower level development. And I always had the suspicion that kind of lower level development, system level programming, is not only difficult because it's maybe less mainstream, slightly more tricky, but also because C++ is just not a good language. So the first time I learned about Rust and saw the sort of semantics it have, I realized, wow, that's something I always wanted for system level programming. And I would never write ZLUDA in C++. It's just too much pain, too difficult. And I knew Rust, and I always wanted to do a project in Rust. So things I wrote in Rust were sort of small projects. I think never released to like try some features or try something out with the language. So I think this first big mainstream project I did in Rust, and I'm really happy about the language. So language is relatively good for writing system level code. Well, there's some problems with it, like, but I mean, a very small minority, my opinion at least. So maybe don't listen to me, but the build system is really anemic, and so it works well if you have a relatively simple project that is all in Rust. But we have things that are slightly more complex. There's interop there's code gen, and cargo is just not good enough for this purpose. So we can't have our own solution, but would be better if cargo had a real build system. So I actually prefer CMake. I'm one of the few people probably only person who prefers to have CMake or MS Build or anything else other than cargo for building. Cargo does package management, is relatively good at package management, but build system is just not it. But when it comes to language semantics, to the availability of libraries, it's good. That's what I wanted.
Why would C++ be painful? What about the language is a problem?
It doesn't have the feature I want in the language. So I want to have enums, discriminated unions. So I've experienced writing in F# and professional experience writing F# in F#. You are going to use discriminated unions a lot, and a lot of really fundamental types in Rust are expressed as enums, like F# Rust styles enums, where you have not only the value but also data associated with it, discriminated unions. And so things like instruction. This is enum. Statements, directive, pretty much everything in the compiler. And C++ doesn't really have a good support for this. Other things like memory management, much easier once you learn how to deal with borrow checker. It's much easier to do in Rust than in C++. And obviously Rust is not all, not whole world subscribes to Rust's ideas about memory management and object and code safety. So if you look at things like where we have to sort of interact with the outside world, like emitting LLVM assembly, the code to emit LLVM assembly is just every second line is unsafe, but it's okay. Unsafe in Rust is the same semantics or even more strict semantics than C++. So we're still coming ahead with Rust. So it's that's what I want, basically.
So Rust is basically just, at least for you, the better tool for the job.
Yeah, for me it's better C++. So, and as I said, Rust is not perfect. There's some areas where it's just unusable, like writing GPU side code. So C++ has, and specifically Clang, has all those little attributes that are useful for me. So, and things like support for address spaces. This is very niche features, but I want them for writing GPU code, because if you look at ZLUDA compiler, certain functions are implemented as calls to full-blown functions in a LLVM module to which we link to during compilation. And this LLVM module, it's written in C++. We write C++ compared to LLVM. And you cannot really write this sort of code in Rust because it doesn't have good support for writing GPU code.
Fair enough. I thought you were going to say more there, but no.
No.
The delay sometimes throws me off when people are going to stop talking.
Yeah, you're literally on the other end of the world, so must be a fair bit of delay.
Yeah, I can make it work though. I've made it work so far, so it hasn't gone horribly bad. One thing about the project itself, I don't think you really talk about this anywhere, but like the choice of license on the project, and again, neither of us are lawyers, so don't get on our case about any specific points. But why? Because it seems to have two licenses attached to it: the Apache and MIT license.
Yes.
Why is there two licenses, and why those licenses in particular?
So I want my software to be used by everyone.
Fair enough.
For any purpose you want. So, and this has been sort of actually comes from Rust community. It's just been popular solution in Rust community to dual license under MIT and Apache licenses. You pick whichever one you want. And as we agreed, we are not lawyers, and this is my understanding that this is the path to be the most compatible with all other open source and closed source licenses. That's why.
So your goal is basically just making it so people can actually use it, rather than, ensuring some free software perfection about the software where, it's everyone that uses it has to also be free software, all that sort of stuff.
Yes.
Actually, while we're actually down this route, what is like your general stance when it comes to like open source and free software? It clearly from this you're like
Huh.
more in favor of the open source side, but do you have a sort of position you stand on more generally?
So my thinking is, and this comes from working at relatively big companies.
Mm-hmm.
If you want your software to be used, the way to go is to use MIT or Apache license. If you're licensing under GPL, big companies will not touch it unless it's something that is extremely critical, like Linux kernel.
Mm-hmm.
Like those companies have explicit policies that, hey, if it's MIT or BSD or Apache, then you can use it install on your computer, link to your software. If it's GPL, not really. And before release, and this is even for internal stuff. For external stuff, there's usually, or rather, stuff that is being released from within the company. There's going to be a legal review, and they will check if you're using something that uses GPL. And if it uses GPL, then it's probably not going to be released with GPL. So, like maybe it's your goal, so the corporations are not using your software. Then I would even just recommend using GPL. That's just, it's not my stance or politic, but this is the reality I observed.
Mm-hmm. Yeah, the Linux kernel was in like a weird position when it came along because it was there to replace the proprietary Unix systems that were coming up, and the BSD world did exist, but it was this weird like mix of proprietary BSD and then 386 BSD was there as well. And I we could just turn this into just me ranting about the early history of Linux because this is one of the topics I really really enjoy. And why the whole like GNU herd thing just didn't work, and why it should have been based on 386 BSD, but then they didn't end up wanting to do that and chucked away that entire project to wait on this mythical kernel that was never going to come around anyway. And then Linux came along before they even started the project, so no one cared about herd after that anyway. Yeah.
Yeah, but just be aware that GPL license stuff has a sort of special position when it comes to licensing in corporations. So they're going to use it, they're going to contribute, but it has to be big enough. So they're going to use Linux kernel. They're going to have their own fork of GDB, which is also GPL license and stuff like this. But if it's something smaller, then a lawyer who is giving you a review is not going to probably give you a special exception for it.
Yeah, if your goal is to make a license, to make a library, just don't even bother. Don't even bother with a GPL style license.
I mean, I'm not going to tell you how you should live your life. It just,
Sure.
If you're maximum usage, then GPL probably not the solution.
So, what is your like background in programming? I don't just mean like your like corporate background. Like, when did you actually start like doing programming? Like, how did you actually get yourself interested in it?
Well, during my first programming lesson at university, I didn't program before going to university. So I hope it's not going to be a letdown. But I always used computers, but was not really interested in programming as such. I went into a computer science degree because I was broadly aware that you can have a good life if you have a computer science degree. Whatever you do, programming, security, databases, it's going to be fine. Those were different times. That was oh wow, so long ago. Well, I'm not going to say, but long time ago. It's still I had understand that it's going to be great, and I was actually um, how do you say, overwhelmed? Maybe not the best word, but I did not see myself as a possible programmer because my thinking was that, programming extremely difficult. Every programmer has this sort of galactic brain, and the tools they are using are really high technology, and everyone is excellent. And I started programming, and what I realized that all the programming languages are old garbage from 30 years ago. Programmers, they cannot program a FIS bus. So it doesn't matter if I'm bad at programming. It was extremely encouraging because I realized it doesn't matter if I'm really bad at programming. Other programmers are even worse. So my bad code is not going to make things worse on average. So yeah, let's start programming, and it was interesting. Um, that's how I became a programmer. I actually found my passion for programming during when I was studying for computer science degree.
In that first programming class you did, what language were you actually working with?
My first programming lessons
Was it something
was
sense?
C.
Okay.
C.
Okay, it's a sensible language because I've heard some real weird answers from people before where it's like Objective C or just other random things that don't make any sense.
Right. So I learned a number of those languages. And I don't think I'm using many of them. So I learned C, C++, Ruby, Python. I did so C# I learned by myself, and this was my first professional language I used professionally.
Okay, so all completely normal and sensible languages. I started with Java.
Oh yeah, so when it comes to oh yeah, I learned some Java. we learned Prolog.
Prolog.
But I remember nothing about Prolog.
I don't remember that Prolog existed.
Yeah, it's fairly interesting in its niche. But I wouldn't be able to write anything in Prolog nowadays.
So now is ZLUDA like your main focus at this point?
Yes. And my journey has been when we want strange languages was sort of C#, then F#, then assembly, then ZLUDA, which is Rust and C++. No, there are some, and in between there are OpenCL and C4Media, which you definitely didn't hear about, and none of your listeners heard about, but it's great language. Actually, unironically, it's a great language for writing code for Intel GPUs. It's a dialect of C++ for writing Intel GPU code, and it's really good if you want to do just this. It's mainly used internally at Intel.
Oh, okay, that makes sense then.
But I think they did some public releases.
How do you spell the name, by the way?
C for no, I think it's C for metal nowadays. Previously called C for media.
Yep. Okay.
Has nothing to do with Apple Metal. Everyone asks this question. Nothing to do.
C for Metal is a programming language allows for creation of high-performance compute and media kernels for Intel GPUs using an explicit single instruction, multiple data programmer, blah blah blah. OpenCL and SYCL applications use implicit simmed program model, blah blah blah. Okay, I don't want to read all this.
Yeah. So by the way, if you have an Intel first-party library that has GPU code, check which language does it use. If it's written in C for metal, those people know what they are doing. If written in something else, probably not.
Oh god.
No, but they're trying to include C4 metal in DPC++ as a different mode of programming. It's called now eSIMD, explicit SIMD.
Okay.
But CM is still more ergonomic if you just want Intel GPU code. eSIMD has the advantage that it interops much better with the normal DPC++ code.
So let's actually get back to like the project itself. When you wanted to sit down and actually start working on a project like this, like where do you even start with something like this? Like, you see the API there, you see you have a GPU. What do you even do to start getting anything, doing anything?
Start with the so in this case was starting with trying to understand what CUDA is, because it was my first CUDA project. I mean, I know what CUDA is, but I had years of experience writing. Oh, this was also, I didn't mention, the secondary goal of this project was to actually understand how CUDA works, or how you write CUDA code. So at this point, I had years of experience writing Intel GPU code, but Intel GPU slightly niche. It's always worth it to understand what is the competition doing, how do you write CUDA code. So firstly, understand how do you even simplest things with CUDA, and then the goal has been, the first goal has been an application that does simplest thing possible, adds 2 numbers on a GPU. So it still needs to do a fair bit of setup. So get a context, load the source module, allocate memory, all those stuff. So look with tool like, so on Linux you have tool like ltrace, where you can log all the interactions of your application with certain libraries. So one of the first things to do was understand what sort of host functionality has to be implemented, and think really hard, can it be implemented in terms of Intel GPU? So all this host functionality. So don't think big. Don't think big. That's what worked for me. It was just a simple application. Because it was a research project, I had no goals to have complex things running. If I had 2 and 2 returning 4 on the GPU, I would be successful. So I have a simple application. I know what are the interaction. Obviously, it was a lie because I didn't know about Dark API at the time. But and then I look at those calls, and each of them, there's like, I don't know, 10 of them, and I know, okay, all of them can be expressed in the terms of Intel level 0. And this is host code interaction. Since I have experience with writing GPU code, I know there's also the GPU side code. So next step was try to understand what is the format of the NVIDIA GPU code. Is it some kind of intermediate representation, or is it some kind of specific architecture-specific assembly? I mean, depending on the level of complexity, either can work. And here I was lucky because, as I said, NVIDIA is competent, and they have virtual assembly called PTX. And this is a text format. So I have a text format, and this text format contains, and it's somewhat abstract, at least from my perspective. So it's virtual abstract representation. It's not written for a specific assembly, but it's going to work after compilation with any CUDA GPU. And I look at the instruction set, and actually, good thing NVIDIA documents the PTX format, and I look at those instructions, and all those instructions I'm familiar with, and I know they're going to work on Intel GPUs, some things like load memory, store memory, do multiplication, do addition. All those things are going to support that on Intel GPU. And I was still thinking small. So, okay, I have my very simple module in text format, and I have my host code. So it looks possible. If it looks possible, then I started implementing, starting with the PTX, with the compiler, because looks relatively easy, but as I start implementing, there are complications.
Mhm.
And the way to implement this sort of classical compiler design, you have your text code, you start by parsing it using a parser generator. In my case, it was a Rust library called lalrpop. It's that's the name.
Sure.
So, yeah, it comes from it comes from abbreviation of this kind of grammars it can parse. It's not super fun, but library is good. No, this is a solid library, and I start parsing those things, and then once you have things parsed, you have in sort of in memory representation of the source code. You now start writing your transformation passes, and every transformation pass makes it slightly closer to your target. So I didn't even think about what my target is going to be. At first, I thought maybe I can compile it straight to the Intel GPU instruction set, but relatively early I decided no, it's not going to work. I'm going to compile it to SPIR-V, which is a bit more abstract, much easier to compile for, which was the right choice. So okay, I'm going to compile to SPIR-V, and now in every compilation path, I try to make it a little closer to what SPIR-V is expecting. And it sounds simple, but there's a fair bit of weird behaviors in PTX format. There's entirely, for example, there's entirely too many address spaces. On GPU, you are generally going to have like four different address spaces: global memory, shared memory, private memory, generic memory, maybe constant memory. And PTX has like 7 or 8, and even in a simple kind of 7 or 8 different address spaces. Some of them are, I mean, if things were designed from the ground up, are really not necessary in the current world, but they exist, and you need to have some way to translate them to address spaces that are available in SPIR-V. Some instructions have no direct replacement in SPIR-V, so you have to replace with a series of simpler instructions, this sort of thing, and it took a long time. So it was almost a year just to have translation that actually translated correctly and worked. So if you're attempting something like this, I don't have any advice other than start small and never give up. Because so I gave up like 3 or 4 times. One of those things was I said previously, dark API. First time I encountered this. Another time was when I was very technical. So I did one pass that was completely unnecessary, translation to SSA format. And I realized that, well, it's completely unnecessary. LVM and SPIR are going to do this for you. You don't have to do this.
What is the SSA format?
Single static assignment. This is sort of representation on which compilers operate, optimizing compiler, because this sort of compiler that is inside ZLUDA is not an optimizing compiler, it's just translation.
Right.
So it's completely unnecessary. And there's some 2 or 3 other things I don't remember, but I do remember just giving this project a rest for a week or 2 several times and still coming back to it.
When you said this was your first CUDA project, the first thing I instantly thought of was the Linus Torvalds Linux email. It's just a hobby project. It won't be anything serious like GNU.
Yeah. As I said, I didn't expect it to be any big. Was the main reason I wanted to do this. I wanted to learn about level 0 and CUDA, mainly about level 0, because it was new for all of us at Intel at the time.
So it was at least initially just basically a hobby project to like learn how this works.
Yeah.
But it sort of came along, to some extent and became something a lot more than that.
Yeah, it was even when I was joining AMD to work on this project for the first time full time, we didn't know if it's going to work. So we sort of expected that it's going to be either going to work and it's going to be great, or just as likely it's not going to work. We're going to run into some kind of impossible roadblock, and in this case we are going to release the updated ZLUDA for AMD that doesn't work for some reason, but with explanation why it doesn't work. So it's anyone can read the source and learn from it.
Yeah,
I didn't expect. Nobody expected it's going to work, but it does. Performance is actually not bad.
Yeah, I didn't bring up the AMD stuff earlier because I wasn't sure what you can and can't say there, because I'm sure there's, at least judging by what you have publicly said, there certainly were issues that have gone on.
Yeah, so I can only repeat what happened. So I worked as a contractor for AMD for 2 years. Towards the end, I released the source code. AMD decided that they shouldn't have allowed me to do so. It's not legally binding. We rolled back the code to pre-AMD version, and we are starting again.
Yeah, that's. I'm sure there's a lot more there that you would like to say if there weren't issues there, but
maybe one day. But
I certainly won't push you on that, because I'm sure there's certainly some legal issues there that you don't want to you you avoid getting sued by NVIDIA. You don't want to get sued by AMD.
So it wasn't that. So what was interesting about the situation is that something I learned. There's so many internet lawyers who want to prosecute the case in front of internet judges. So one reason why, the main reason why I'm trying to dodge this topic is that it's going to bring internet lawyers into the comment section. And
I see.
Sorry, it has been already handled by actual lawyers.
Yeah.
So it's not going to happen. And another thing is that there's certain demographic of people who blame NVIDIA for everything, even if NVIDIA has nothing to do with things, at least to my understanding.
Yeah, I've definitely seen a lot of those internet lawyer comments myself. If you go on Reddit, you'll see plenty of them. Like, oh, well, I even just in the GitHub discussion you had, like, there were people arguing there, like, what was the position of the person who told you to take the thing down? Are they at the correct level of the chain to do that? Like, you're not, even if you were in the right, like, I can't imagine you're in a position to, like, go to war against AMD. Or even want to do that.
No, I'm not. AMD is a billion-dollar company. I'm not going to fight them. They have lawyers. They have PR department. Like it's not helping anyone.
Yeah, it's much better to just comply with whatever
Yeah,
whatever they want to reasonably get you to do, and then just
yeah,
go from there.
yeah. Focus on the technology. Focus on the nice things we can build. All the applications that we can have running on your GPU.
Mhm. So, what is the current state of things?
So current state of things is very little works. So currently, I don't think even the whole. So this is the situation as of today. I don't think even the whole whole project builds, because it's being written from the ground up,
Mhm.
starting from the most basic things like even parsing of the PTX. So we have a new parser, and then this new parser, the way it works has effect on the rest of the compilation.
Mhm.
So I rewrote the parser, rewrote the compilation passes to be nicer, simpler, and recently finished writing the code responsible for emitting LVM bit code. So there's a number of unit tests inside ZLUDA, and the unit test works by unit test for the compiler. So compiler takes a simple handwritten PTX module, compiles it, check if the result is as expected, and there's like 90 of them.
Mhm.
So those tests work, compiler works, but we don't have host code working, and that's the next step. Have the host code working, have some other tooling around the project working, and once we have host code, has some of the necessary tools, then we'll start focusing on the specific workloads.
Mhm.
The first one is going to be probably Geekbench, because it's relatively simple, and then work on those machine learning workloads. So LLMC. LLMC is probably going to be the first machine learning workload that works.
Mhm.
With some caveats. Flash attention support will have to wait a little bit. But yeah, LLMC is the first goal, first milestone.
So now that you've done a lot of this work, like in the past, now you're doing a rewrite. What is it like? Other things that you've maybe learned from that experience that maybe are going to make things easier now? That because as you said, you started it. It was like your first attempt at doing this. I assume there's a lot you've learned from doing it at least once.
Right. So one big lesson: don't trust AMD things to work. It might sound funny, but it was extremely stressful situation. One of the first workloads I did, sort of when I contracted for AMD, was a closed source application. I don't remember which one, either 3ds Zephyr or Reality Capture. And so I enable everything that is required for this application, both host code and in the compiler, but for some reason it doesn't work.
Mhm.
And since it's closed source application, it's relatively tricky to debug, but eventually I found the kernel that is producing incorrect data.
Mhm.
And I run this, so I extract this kernel and the data it operates on, and I run it both on the CUDA stack and under ZLUDA.
Mhm.
And it works correct. And it works correct on both every time. But for some reason, the same kernel fails when run inside the application. And at this time, I'm starting to panicking a little because it's, impossible situation, impossible to debug. It should work. It just defies the logic and the laws of physics. And I tried it both ways. So I ran the whole workload on ZLUDA, and because I thought, maybe earlier kernel under ZLUDA is computing things wrong, and I run it on both source from CUDA, source from ZLUDA, and try it ZLUDA to CUDA, CUDA to ZLUDA, it all works well, gives right result.
Mm-hmm.
And purely by luck, I realized that there's a bug in AMD host code. For certain memory copies,
Mm-hmm.
it copies them incorrectly. It was my first revelation. Do not trust host code, even if it's simple mapping, even if it looks simple. Do not trust that AMD host code is going to work correctly. Always double check. So there's, it sounds pessimistic. There's not so many cases, but generally, if it's something that has to do with textures, then double check if you're using heap. So that's what I learned. There's some other lessons, and they're very ZLUDA specific, and it was actually somewhat frustrating starting from this point 2 years ago, because I look at my code from before the rollback, and I look at this compilation path, and I think, well, that's wrong. That's wrong. There's better ways to do this. There's better ways to do this, but I have to fix all that other code before I arrive at this.
So you can see where the goal is, but there's just
much
to get
I
there.
remember. I just remember. Oh yeah, I got rid of this part because there are better ways to do this, but I have to live with this again.
But hopefully the second time around you can get there quicker. Like now that you
it's much quicker right now because firstly because the workloads are different. So one thing I did not mention that we're getting rid of, I mean, somewhat sadly, I have mixed feelings about this. We're not going to do ray tracing because ZLUDA has had an implementation of optics. Optics is NVIDIA's framework to do ray tracing, and it's very complex. During my contract work at AMD, I think optics took, I don't know, almost a year. It was very complex. Not only optics itself, but also applications using optics. So the goal has been Arnold. It's closed source, very complex rendering solution. Debugging it was a lot of effort. So it's going to be so much faster without optics. So much easier.
It would be cool to have it, if you had infinite time.
I know. I agree.
Money,
I agree. Yeah. So one of the things. So as I left AMD, released ZLUDA. So something that became really clear really quickly was that there's a lot of interest in machine learning workloads.
Right.
There's relatively little interest in sort of professional graphics workloads. So I've been focusing on. So there's a time when I left AMD and had nothing else lined up. So I was still working on ZLUDA, but focusing on the workloads for which there's no commercial interest. And this, I almost got GameWorks. Well, I got it running in one application, but never merged the code. And then things similar to it. So like, I don't remember. There's this suit for 3D photogrammetry. I don't remember what was it called. So also has been requested, but there's no commercial interest in it.
Right. But I like to just most people will describe NVIDIA at this point not as a GPU company, they're an AI company, right? Like I like to call them a machine learning shovel company. During a gold rush, don't dig for gold, sell the shovels. That's what NVIDIA does.
Yeah. That's true. If you look at the machine learning market, machine learning hardware market, there's two markets. There's NVIDIA market and non-NVIDIA market. And a lot of people want ZLUDA for machine learning because they want, okay, not by the means of hardware, but the means of software, take part of NVIDIA market, because NVIDIA market is much bigger than non-NVIDIA market.
Yeah, and that's just not going to change in the real world. Like it's like no matter what AMD or
I mean,
Intel does.
AMD making effort, and AMD is, I think, closest because, as I said, they made the right strategic call to make their APIs close to NVIDIA APIs. So maybe the closest. The problem is their execution is just not good. And purely talking about software, there's also some hardware choices, some design choices they made in the hardware that make porting from CUDA to heap more difficult than it should be.
Is there anything you want to get into there, or?
Yeah. So, and it's no secret. Do we have a drawing board? Because I need to draw it in Jitsi.
I don't know if Jitsi has one actually. I don't use.
It would be helpful if it had one.
Yeah,
there's show whiteboard.
Okay.
Excellent.
Yeah. Beautiful.
Okay. So core difference between CPU and GPU is that if you have a hardware GPU thread, it's going to operate on a vector of data. What it means is that you have your CPU, and CPU. How do I draw? Well, okay, that's what I meant. Give me a second. Okay, this one. So, okay, you have CPU.
Okay.
CPU operates on a single element at a time. So you add 2 plus 2, you get 4. Single element at a time.
Right.
GPU operate on a fixed vector of elements. So in this example, this is GPU where the instruction set had a width of 4. So maybe there's 1, 2, 3, 4, and another, I don't know. Where's the eraser? There's no eraser on this thing. I think I have to. Well, whatever. There's 1 plus 6, 7.
Yeah.
And the result, well, we'll leave it as an exercise for our readers, watchers, listeners. But it operates on a vector at a time. This is key difference. This is why CPU code is not going to be efficient when just taken and run on a GPU code, because you're going to use only one element of the vector. And that's why only some workloads are efficient on GPU, because you need to be able to vectorize your things. And in this example, you have width 4 of the vector, and this is sort of the most basic parameter of your GPU. If you look at all NVIDIA GPUs in the history that are programmable with CUDA, and probably every GPU in the future, the width of the vector, the number of elements you operate at the time, is 32. And AMD, for some reason that is impossible to explain. Okay, I'll explain in a second. But for reasons that are, maybe I shouldn't explain, it's going to sound silly, but this is explanation I received inside AMD. So AMD has really two architecture. One architecture that is not meant for compute, that is meant for gaming, has width 32, which makes it easy to port compute code, and their compute architecture is difficult to port compute code. So,
are we done with the whiteboard, by the way?
Are
we done with the whiteboard, by the way?
Come again?
Are we done with the whiteboard? Do we need that on the screen?
Yeah.
Uh.
I don't know how to close it either.
Unpin? What? Now the whiteboard's
Yeah, okay.
just a
You
part of
suffer
the
with
thing.
this whiteboard, and I continue my
Whatever, we've got a
explanation.
few minutes left of the show anyway. It's gonna just be a broken layout. It's fine.
Okay, yeah. So on AMD GPUs, you compute GPUs have with 64.
Mhm.
It's relatively difficult. Well, it's not impossible, but it's extra difficulty to compute CUDA code with written for vector size 32 to AMD GPUs with the vector size 64.
Mhm.
And if every AMD GPU had vector size, what's called warp size 32, it would be much easier to port, much easier. But what I learned at AMD, there's a guy who has a spreadsheet, and according to his spreadsheet, warp size 64 is better for central workloads than warp size 32. And that's why AMD spends millions of dollars porting from warp size 64 to warp size 32.
Okay.
Otherwise, it would just replace the names and it should work.
If
it's 32 to 32.
You know, I don't think I ever had a visual demo in the middle of a show before. That's certainly a first. Oh wait, no, I did have a game dev on who did one once. This is the second time. I've not had a whiteboard though. A whiteboard's a new one. I'll have to.
Yeah, but I think it's nice.
It's a nice change. I like it. I've done like 250 of these or so, and finally there's something new and weird.
So by the way, so previously ZLUDA has the two modes to run. Expected by CUDA warp 32 on hardware warp 64, but it was time-consuming feature because it sort of applies to every layer of ZLUDA, both compiler and both host code. So we're leaving it out. And AMD announced that they're merging those two architectures into one. And I mean, I don't have special knowledge, but I expect it's going to be warp 32 to be similar with NVIDIA. Otherwise, it would be self-sabotage, not using warp 32. Like, even if it's not efficient in its hardware sense, it's much more efficient when porting the software. And porting the software is the bottleneck.
Right, even if it's faster, if no one's writing software,
yes,
making use of it, like, it doesn't matter.
Yeah. Sadly, we live in the sort of CUDA-shaped world when it comes to GPU compute, and that's the objective reality.
Well, on that note, I guess we could start like wrapping things up. So let people know where they can like find the project. I know you've got a Discord server linked here as well, and everything
we do.
else.
We do.
How active is that? I haven't gone into it myself.
I mean, it's fairly active. So what else? So can you put the link to GitHub and Discord in the description?
Yeah, I can do all that. Yeah,
because there's no like nice and easy link to it. Please do. Okay, so we have a Discord. So I was worried at the beginning that there's either going to be, like, I don't know, 3 people and it's going to be totally empty, or it's going to be 3,000 and I will be spending time moderating the Discord. But no, there's I think like 100 or 200 people.
Okay.
It has healthy level of activity. It's nice. And I encourage you to join, unless you're one of those people from comment sections who is going to write really ugly things about NVIDIA or AMD, about Intel. In this case, please do not come. But if you're a normal person, please do. Like when I have something working in ZLUDA, I'm going to share it first on Discord, and later when I have more things batched together, then I'm going to write a news. So if you want to build a bit closer to the development as it happens, or you have some questions, then please join Discord.
So if somebody wants to like get involved with the project, head over there and head over to the GitHub and just
yeah. If you want to get involved, look at GitHub, join Discord. It's probably so we are not getting so many external contributors. I think one of the reasons
that project.
And it's sort of not mainstream programming. If it's something web related, you are going to have a much bigger pool of developers who can contribute. GPU development, much more niche. So it's not like we are overwhelmed by contributors. If you want to add something, then you will be a really special person in this project.
Oh, there's 12. Okay, yeah, there's 12 contributors listed. Yeah, you will be a very special person.
Even if you cannot contribute code, then if you can contribute, I don't know, changes to the documentation or documentation itself, very welcome. I'm not a native English speaker, so you might have an advantage over me and ways to improve this project.
It is really normal for a project to have, a big drop between their core contributor and then the second top contributor. I have not seen a distribution like this before, where you're like 400,000 total lines of code added and removed. The next person is 2. You will be a very special person if you write like a serious patch for this project.
Yeah. If you contribute 20 lines of code, you can probably be.
You'll be the second biggest contributor.
Yeah.
So, is there anything else you want to direct people to, or is that pretty much just it?
I think that's it. Yeah.
Awesome.
Oh yeah. One more thing. Watch the next episode and previous episode of this podcast.
Yes, do that. I'll do my outro and then we can sign off.
Okay.
So my main channel is Brody Robertson. I do Linux videos there 6-ish days a week. I did a video on ZLUDA coming back, so if you've not seen that one yet, go check that one out. It'll be out. It'll be like 3 weeks old by the time this video comes out. So I don't know. If you haven't heard about it coming back yet, go watch that video. I go over the blog post to go over the history of the project, all that fun stuff. If you want to see my gaming stuff, that is over on Brody on Games. I stream there twice a week. I also have a reaction channel where clips from that stream go up. So if you want to go over and watch just clips of the stream, do that as well. And if you're listening to the audio version of this, you can find the video version on YouTube at Tech Over Tea. If you'd like to see the video version, it is on YouTube, Tech Over Tea. I will give you the final word. What do you want to say? How do you want to sign us off?
Well, I finished my tea. It's time for another tea.
That's a good plan, actually.
That's it.